In this video, we're going to look at some examples of trigonometric integrals. This should not be confused with trig substitution, which is the next topic. This is, in fact, a topic which might have been covered in your first semester calculus, at least in part. But we'll probably do a little bit more, so that hopefully everybody has something to learn here. So let's get started. Suppose we face the integral of sine squared cosine cubed. Well, this kind of problem, whenever you've got a number of sines and cosines like that, often you want to make either a sine or a cosine substitution. So first thing to do is to try to isolate like a cosine theta d theta or a sine theta d theta, and if you can do that, that suggests that that's going to be your du, which means your u is going to be like, well, sine. So that's good, but that we'd like to convert to sine. Of course we can do that because cosine squared is 1 minus sine squared, right? And so there you have it. And so this is, just a basic u substitution aided by trigonometric insight. So we've got sine squared times 1 minus sine squared, which is u squared, times 1 minus u squared. This is my du, since sine theta is u. And there you have it. That's u squared, and u squared times u squared is u to the fourth, so u squared minus u to the fourth, which integrates to 1/3 u cubed minus 1/5 u to the fifth plus a constant. Then you go back to sine, and there you have it. That's an integral. So that's pretty typical of how to do these sort of problems. It's a combination of, use of the right trigonometric identity and just trying something. Now this one here, there's a couple different ways to do it. I'll show you the way I like the most. If we have sine squared times cosine squared, we can rewrite that as sine times cosine quantity squared. And then we remember sine times cosine remember sine 2 theta is 2 sine theta cosine theta, right? So 1/2, so this is really 1/2 of sine 2 theta. All right, and then squaring gives me a 1/4, and I get sine squared 2 theta, but we then know that that is 1/2 1 minus cosine 4 theta. Because remember, generally speaking, I used a beta just to give us a way to look at it. Sine squared beta is 1/2 1 minus cosine 2 beta. That's not cosine squared, that's a cosine of 2 beta, okay? And make a beta equals to 2 theta substitution, and that 2 beta becomes 4 theta right here. And the reason to do that, of course, is that, well, now we've got something we can just integrate by plain old garden variety u substitution, right? So that's an eighth, pull that eighth out. Integral of 1 is theta here, and integral of cosine 4 theta is 1/4 sine 4 theta. The minus comes down, and there you have it. There are other ways to do this integral which make it more complicated, but I like that way. Let's see here. I'm still fighting with my stuff on my desk. All right, here. Stop it. One thing at a time, one thing at a time. All right, come on. Good grief. I'm afraid I'm also going to push stuff off to the floor if I'm not careful. Make sure I have not gotten out of frame here. No, okay. All right, so next up, integral sine squared 1/t t squared dt, the t squared down here. Sine squared of 1/t divided by t squared, integral of that, with respect to time, or t. And so here, we first make a substitution. We have to recognize that dt over t squared is a derivative of 1/t. Well, there's a minus missing, right? So if we let theta equal 1/t, then d theta is minus dt over t squared, which gives us the integral of sine squared theta with a minus out front. But this is a pretty standard integral, which we can solve if we remember the half angle identity, namely that sine squared is 1/2 of 1 minus cosine 2 theta d theta. This is something you must have ingrained in you in this course. This is something that will come up probably a dozen times as we go on, if not more. All right, so then we can integrate that using basic substitution, or just straight integration. That gives us minus theta over 2, and 1/4 sine 2 theta plus a constant. Now if you doubt me, differentiate this, and you'll get back what's up here again, all right? And then, of course, to unsubstitute the theta substitution, we get minus 1 over 2t plus 1/4 sine of 2 over t plus a constant. There's another example for you. Let's move on to example 4. Keep in mind, of course, that this is a video, so you can pause it and work it out for yourself, and I would encourage you to do such. As I have mentioned, math is not a spectator sport. You must work it out for yourself. I'm just trying to give you some pointers here. And of course, these examples are also posted in PDF form online for your convenience. In addition, of course, you have a textbook which you could look at. In fact, I would encourage you to get a hard copy of your textbook. And sometimes it doesn't really matter if you have an old edition or not. You can get an old edition of a calculus book for $5, $10 easily. And sometimes the older editions are better anyway. Let's see here. Integral of cosh cubed. Oh my goodness, what's hyperbolic cosine, right? So the key about hyperbolic cosine is it obeys this identity. Cosh squared minus sinh squared is 1. So I'm going to pull off a cosh x dx. I'm going to think of that as being the differential, the derivative, if you will, of sinh, right? Because the derivative of sinh is cosh. So this is like a derivative of sinh times dx. And then, of course, we got the cosh squared. All right. But cosh squared we can convert to 1 plus sinh squared. And then if we let u equals sinh x, then du is cosh x dx. So that's my du. That's why 1 plus u squared. I got 1 plus u squared du. So then we can integrate u plus 1/3 u cubed plus a constant. And there you have it. Sinh x plus 1/3 sinh cubed plus a constant is the integral of hyperbolic cosine cubed. And let me just pause here, and again, in case you didn't see it before, to talk a little bit more about hyperbolic functions. The above is a hyperbolic trig integral, but I included here because the technique needed to solve this is nearly identical to the trig case. I mean, technically this little bit is titled integrals of trig functions, but to me, hyperbolic, trigonometric, and trigonometric functions are more or less the same thing. There are many, many strong analogies between the two. Alright, so in fact, cosh is defined to be that. You can actually show that cosine is 1/2 e to the I theta plus e to the minus I theta, the so-called imaginary exponentials. And you can show also that sine theta is 1 over 2i e to the I theta minus e to the minus I theta. Perhaps you haven't seen these before. These are writing sine and cosine in terms of imaginary exponentials. Not everybody covers this in calculus, but they should. Now we have the derivative of cosh of sinh, and derivative of sinh is cosh. By the way, the imaginary exponential formulas here follow from what's known as Euler's identity, which is e to the I theta is cosine theta plus I sine theta. Now, anyway, I'll tell you more about those later, but I mean, you don't have to know this, but I think it's useful. Anyway, derivative of cosine is minus sine, derivative of sine is cosine, you already know that. Cosh squared minus sinh squared is 1, cosine squared plus sine squared is 1, 1 minus tangent squared is hyperbolic secant squared. In contrast, 1 plus tangent squared is secant squared, right? There's a lot of very similar but just slightly different things going on here. To see that the derivative of hyperbolic tangent is what it is, here's a sample calculation for you, right? So, quotient rule, cosh squared minus sinh squared is 1 over cosh squared. Well, that's hyperbolic secant squared. I'm probably off the edge of the universe here. Let me scroll up a bit. And there's other things, like if you calculate cosh x times sinh x, you can get 1/2 sinh 2x, just like it works with sine and cosine. And finally, just a little bit, and I'll stop talking about the imaginary exponential. By the way, you can derive the derivative of tangent theta as secant squared through a very similar calculation, right? Hopefully you saw that already in Calculus 1. But I mention these imaginary exponentials in part because they're a very useful way to derive trigonometric identities. I guess it's not such an issue for you guys since you have open book tests, but who knows? Maybe you'll find yourself in the residential classroom where you have closed book tests. I don't know. Who knows? It could happen. Anyway, so cosine theta sine theta is this times that. You pull out a 1 over 4i, you multiply the exponentials, and it multiplies just like you'd expect. E to the I theta times e to the theta, e to the 2I theta, and this times that is e to the minus 2I theta. The e to the I theta, e to the minus I theta are reciprocal. They cancel out to give you e to the 0, which is 1. These multiply to give you e to the 0, which is 1. So this is just straight multiplication, distribution. And so these cancel, and those leave you with e to the 2I theta minus e to the minus 2I theta. Lo and behold, again going back to the star formula, replacing theta with 2 theta, you can say that that's sine 2 theta. So this gives us that cosine theta times sine theta is 1/2 sine 2 theta. Something you should know, but if you really understand the star formulas, you can actually derive it by algebra. Something that you probably couldn't do without imaginary exponentials. Just saying. Moving on. This advertisement for imaginary exponentials is now done. It is doubtful that I test on imaginary exponentials in this course. Anyway, but would we test on trigonometric identities? Oh my goodness, I do think that is very much possible. Because you need to know trigonometric identities to do integration, all right? You'll see. Well, let's see more. Tangent squared, integral of tangent squared ax plus b. So we're going to make a theta equals to ax plus b substitution. When we do that, d theta is a dx, so that gives us tangent squared d theta over a. All right, if you like, solve for dx. dx is d theta over a, I plug it in. Then we trade our tangent squared for secant squared theta minus 1, because you remember tangent squared theta is equal to secant squared theta minus 1. Well, this is wonderful because secant squared is a basic integral. We know the integral of secant squared is tangent. The integral of minus 1 is just minus theta. So there you go. 1 over a, tangent theta minus theta plus a constant. Then plug back in the theta. And we got it. And then this last step right here, I just notice that 1 over a times minus a just gives me minus x. And then I've got the 1 over a tangent ax plus b. And then if you look at it, I've got a minus b over a plus a c. So rather than writing minus b over a plus c as my constant, just write c tilde. Because it's just, just a constant, so I might as well just lump all my ugly constants into one uglier constant. But of course you could have also written minus b over a plus c. That would not have been wrong. It's just, if we have a bunch of constants, we can reduce the clutter and just write one. In that sense, additively. If they're multiplicative, you can't drop them. Here's another one. Integral from 0 to pi over 2 of 2 minus sine theta quantity squared. Alright, so here I have to multiply this out, like so. And after doing that, that's integrable without further ado. And this guy, we're going to use the half angle formula on to deal with. Alright, so this and that integrate to this and that. We evaluate from 0 to pi over 2. Great. This one, we're going to integrate to 1/2 of 1 minus cosine 2 theta, evaluated from 0 to pi over 2. This works out to 2 pi minus 4. And so this integrates to theta, that integrates to minus 1/2 sine 2 theta. That 1/2 comes because there's a 2 theta here, right? And if you differentiate this, you get back to that again. This half stays up front. And then we evaluate from 0 to pi over 2. Sine of 0 is 0. Sine of 2 times pi over 2 is sine of pi, which is also 0, so this contributes nothing. That, on the other hand, contributes pi over 2 times 2, gives me... Wait a minute. What? Hey. Not cool, folks. Not cool. That's pi over 2 times 2. Times 1/2, not times 2, right? I was thinking 2 times pi over 2 when I wrote that 3 pi there. Well, we've come to my first error. It won't be my last, but this is not correct. This should be what? All right. Looks like I'm gonna have to give me a B minus on this talk. Oh, I tell you what. Goodness gracious. 2 pi minus pi over, plus pi over 4 from this one. Minus 4 would be the answer. And let's see, if I wanted to combine the pi's, what do you got? How many fourths is that? That's 8 fourths, right? So 9 pi over 4 minus 4. There you go. Or if you, I'm going to stop. Anyway, there's an answer that's at least not wrong, I think. Do let me know if I have wrong answers. I do appreciate feedback. I am human. I do make mistakes. All right. Okay, so integral of sine theta, sine 2 theta, sine 6 theta. So there's a trigonometric identity, which gives you that the product of sines is 1/2 the cosine of the difference minus the sum, like so. So this is a trigonometric identity, which I'll talk about down here in a minute. Setting aside the issue of where on earth that came from, that gives us integral of 1/4 times 1/2, which is 1/8 sine 4 theta, and that integrates, when we integrate that, we pull out a 1/8. So we get a minus 1/8 times 1/2, which is minus 1/16 sine 8 theta plus a constant. There you go. Now, of course, to derive, well, I used anyway, that sine of A times sine of B is 1/2 of A minus B minus cosine of A plus B. And the fact that cosine of minus 4 theta is cosine 4 theta, since cosine is an even function. Oh yeah, because 2 minus 6 is minus 4. So, but I didn't put minus 4 there, I put 4 because, well, cosine of minus 4 theta is cosine 4 theta. And why not think about cosine 4 theta rather than cosine minus 4 theta? Right, because cosine 4 theta is less annoying. Okay, so there's one. Now, if you don't know this trigonometric identity, this problem is like really, really hard. I don't know, maybe you get it with integration by parts. I don't know, I don't want to try. I prefer to know trigonometry. All right, so next up, integral of secant squared tangent cubed. Ooh, scary. So this has got kind of an extra secant tangent sitting in there, so we should pull that out, because if we do that, we know the derivative of secant is secant tangent, so that suggests maybe we can make like a u equals secant substitution, and this would be my du. I got a secant there, I got a tangent squared. I got to convert that tangent squared to secant squared to be successful. Let's see how I do it. That is what I do. So u equals secant x, du is secant x tangent x dx there. The tangent squared becomes secant squared minus 1, because that's a trigonometric identity which we know and love and are just waiting to use. And we got secant times secant squared minus 1, and then I make a substitution. That gives us u cubed minus u du. Integrate 1/4 u to the 4th minus 1/2 u squared plus a constant, and convert back to my secants, and there you have it, integrated. Wasn't too bad, was it? Now, oh, look at this, look at this. Cosine, oh my goodness, cosine to the 4th e to the t of e to the t dt. Well, this first requires a little bit of triage. Let's say we're going to make a u equals e to the t theta equals e to the t substitution. Then this becomes d theta, and we got cosine to the 4th theta d theta. All right, great. So that is cosine squared squared. Yeah, I know. And then that cosine squared we can convert to 1/2 of 1 plus cosine 2 theta, d theta, cosine 2 theta quantity squared by the half angle trig identity. But then you got to square this thing, which is going to bring down a 4th. And when you FOIL this thing out or distribute it or multiply it, anyway, whatever you want to call it, I get a 1. The cross terms give me 2 cosine 2 theta, and then I get cosine squared 2 theta. This I can integrate, that I can integrate, this I got to do the half angle thing on again. So that gives me 1/2 of 1 plus cosine 4 theta, this term right there. All right, and now I finally gotten down to things that I can integrate. All right, and so I do. Well, I clean it up a little bit. I combine things. I get 1/2 plus 1 is 3/2, right? Then I got my 2. I got my 1/2 cosine 4 theta. And then that gives me 3 theta over 8 plus, oh, 2 times 4 is 1. Wait a minute. Oh, no, I'm okay, I'm okay. sorry, I was worried there for a second. But 2 over 4 is 1/2, but then the integration brings it out another half. So that's sine 2 theta over 4. And this gives me an 1/8, but then the integration gives me another 1/4. So 8 times 4 is 32. 1/32 sine 4 theta plus a constant. And it's like, oops, I forgot star. In other words, I thought the answer was theta, but I've forgotten, my home. I forgot where I started from, e to the t. Substitution. So I put back in my theta equals e to the t, and there you have it. That's the integral of that, like that. So it's just a bunch of little steps, one after the other. That's how we do these. Now this one's interesting, and a lot like possibly like one of your homeworks. Integral of dx over cosine of x minus 1. So here we do something kind of sneaky. Multiply by cosine x plus 1 over cosine x plus 1, which is just multiplying by 1, right? And the reason I do that is because then I get a cosine squared x minus 1 downstairs. See, because I get plus cosine and minus cosine, they cancel. It's kind of like rationalizing the denominator or something like that. And but you notice cosine squared x minus 1 is equal to minus sine squared. This is a minus sine squared, right? And so, all right, well, that's kind of close to something I know how to do. Oh no, it's a mystery. How will we finish? How will we finish? Well, I leave that up to you guys, all right? But this you can break up into, a cosine x over sine x squared minus a 1 over sine squared. 1 over sine squared is, what's that? Well, I believe that's a cosecant squared, which minus cosecant squared, I think, integrates to cotangent. So you break these up into two integrals. The one you can do with a substitution, the other you can do because it's a basic integral. It's an integral of cotangent. Oh, excuse me, cosecant squared, which is cotangent. Minus cotangent, I think, but there's a minus here. Anyway, past year, I think you can do it. So I'll leave you with that. I hope you learned something from this. And again, the key behind all of this is to know your trigonometric identities. All right. Anyway, with that, I will stop. Thanks, guys.